and then we can start. Okay, so thank you to everyone who is attending today to this webinar. And today's webinar, we are going to introduce the Pan-European Dataset for Energy System Planning that we have developed in the Mopo project, in a Horizon Europe project. And this dataset has been developed in the Work Package 2 about data component tools, where different partners have been contributing to this data set with tools or data collection. So different institution has participated, and basically the main idea is to cover all the sectors in this data set, which are basically driven the European economy, the energy economy, and also those which are driven the transition of European economy to climate neutral by 2050. So the main idea of this webinar, we are gonna everything has been taken from public sources or public available data sets. We have created different pipelines in the SPINE tool environment that we had several webinars already about the SPINE toolbar and SPINE out, so those which are building this SPINE environment. And we have developed different pipelines to also targeting different spatial resolution and temporal resolution. So the main sectors that we are covering is electricity sector with variable renewable energy, hydro. Also, we have biomass, the gas sector, the fuel sector, industry, transport, buildings. So we are gonna comment everything in detail. The main idea with this webinar today is to show you how where are the main data sources that we have used, how we have processed this data, and how we are using this data in the SPINE ecosystem to create energy system models for planning in a SPINE toolbox. So all the data, or most of the pipelines, have been uploaded to a Zenodo repository. So we have a Zenodo community repository where basically all the pipelines output are there. And also we have a particular repository where we have the full European dataset integrated in this Zenodo repository. In this dataset, you will find all the pipelines. But also you have the individual pipelines in different Zenodo repos. And also in this repo, you will find how to create this model in the INES format, which is the interoperable energy system data specification that we have also developing in Mopo. But we will have a meeting, we will have a webinar specifically for that specific format in the coming webinars. So this is the outline of this webinar. So we will have climate data, variable renewable energy, the hydro electric systems, how to represent those hydro systems, the biomass sector, energy conversion, which is mostly focused in the power sector, electricity and transmission, that right now is focused on cross-border transfer capacity, but and cross-border networks. But we will have more details, or we expect to have more resolution in this one. Also, the gas sector, the cargo transport, and in the last part of this webinar, we will have an introduction to the end-use sectors, which is industry, buildings, and transport. And to conclude this webinar, I will show you a demo on how to use this data set, how to import the data set in a SPINE toolbox, and how to configure your model. So we can move forward to the next part. So basically, we have the main idea of this dataset is to create a sector-coupled model to identify the critical investment and pathways to transition European economy to climate neutral by 2050, so to align with the European climate policy. So we have created basically a dataset which is covering right now 30 countries, so EU 27 plus Norway, Switzerland, and United Kingdom. Basically, the structure right now of the dataset is oriented to planning models. The main idea is to upgrade this dataset to include more operational detail, but For now, the first version is planning oriented. And we have created this dataset where we have basically ETL pipeline. So that means extract, transfer, and load pipeline. So the main idea is we start with raw data. So raw data that comes from the different sectors and pipelines that the other contributor of Mopo have developed. And we use this raw data to make some kind of transformation and import the data into an spine database in SQLite format. That is an intermediate database. And what happens after that? So we will have a model builder that will build the model in the INES, in the Interoperable Energy System Specification format in another SQLite database, but following some user configuration options, but also reading and using as an input data the intermediate databases that you see. So this is what you see basically in this plot. So the blue icon, which are representing the connection to the data sources, the red icon, which is basically the tool that is processing the data, and the pink icon, which is the database where we store the data. Finally, for this slide, so these are the sectors that we are representing: electricity, hydrogen, methane, biomass, and fuels. But also we have networks, which is mainly gas networks, including the potential one of hydrogen, and also electricity. And in the last part, we have the end use sector, which is industry, also with candidate options for alternative routes, transport, and buildings. So let's start with the description of each sector, and basically each task leader will explain you how we obtain the source data that we are using in this dataset to, and also the raw data that we are importing to this dataset in the spine ecosystem. So, Matti.
Thank you, Álvaro. And hello, everybody. I'm Matti Koivisto from Tekniska University of Denmark, and I'll be talking a bit about the climate and weather data, and then subsequently the wind and the solar generation time series and other data we have produced in Mopo. So here, just briefly, we use around 40 plus years of past weather that allows us to look a lot of weather variability for investment, but also adequacy assessment purposes. And then we have also provided some climate projections all the way towards 2100. In Mopo, in most of the studies, we rely on the reanalysis data of the past weather, but we have also made the climate projections available. This is for wind and solar modeling, which I will describe later, but also hydro and temperature-dependent demand utilize the same weather data. It can be mentioned that these data sources are the same that ENSOA uses for the PECD or Pan-European Climate Dataset that they use for the TYNDP and ERA studies. For example, the climate projection selection is exactly the same. And also I will later talk a little bit about the impacts of using Global Wind Atlas, which we use to scale the ERA5 wind speeds for increased accuracy. And maybe on this, just as the final point, is that this data is also accessible online, where you have a GUI, where you can download this data with automatic interpolation, extrapolation, aggregation, and so forth, available in the Mopo project. But if you want to take a look and would like to request access, you are most welcome to also contact us via the website. And on the right-hand side, you can see a little bit how it looks. You can select different types of data and different data sets and so forth, and you have access to the entire time ranges that are mentioned on the left. But I think then we can move to the next slide, if you, Álvaro, please. So then how do we use this weather data? So on our side, on DTU side, we do the variable renewable energy, that's wind and solar generation. And there we use this multi-decade data, including under climate change. We usually have the sort of ERA5 usual hourly resolution, but we can even do up to 5-minute resolution, which we have done for wind in some of the regional studies here in the Baltic case study. And we simulate a lot of power plants across Europe, which is our scope here. We can model in detail the existing installations. We can also look in quite in detail future installations, onshore, offshore, floating offshore, different type of solar, rooftop, large scale, and tracking. And then we provide those multi-decade time series on an hourly basis, assuming different rollouts across the different countries. And for existing, we have a lot of detailed information where the power plants are, what kind of hub heights, what kind of turbines, and so forth. We also do, and I'll get a little bit detailed on the modeling in the next slides, but I wanted to mention we also do the cost data, CapEx, OpEx, lifetime. For all of these technologies, we use as the basis the Danish Energy Agency's technology catalog, and we scale that for some of the technical details that we do there. Also existing installed gigawatt to get the sort of baseline level there into the scenarios that Álvaro will mention later. And also VRE potentials based on land area availability and sea area availability and so forth. How much can the model then build out going forward? We do the wind and solar technologies mentioned here. But maybe then we can go to the next slide, if you, Álvaro, take it there. All of this modeling, we use the Chorus model. This is the same we also use for ENTSOE, for PECD, and other research projects as well. You are welcome to check the website for more details. The code is openly available. And also, as I mentioned, we have this web service where it provides an easy-to-use GUI for people to access and run the Chorus tool. And then I think we can move to the next slide. I wanted to highlight just a few things. Obviously, I have 10 minutes, so it's not a lot of time, but I wanted to highlight a few things. So maybe the first thing here is we use the Global Wind Atlas, our in-house high resolution, up to 1 kilometer resolution modeling tool to increase, in principle, the resolution of ERA5, which is only 30 kilometer. And in this paper mentioned there, if somebody wants to take in more detail, we show that this brings a lot increased accuracy in the Pan-European wind modeling. But I think that's fine. We can move ahead because in the next slide, we can see this in a bit more detail. So on the left-hand side, you will see the ERA5 in the top left with around 30 kilometer resolution. The black dots in this example region are turbine locations. And as you see, if you just stick to the ERA5, you have these very large 30 by 30 kilometer blocks modeling very roughly the actual wind turbine locations. Whereas in the bottom left, you can see when we pull it to the global wind resolution, there's a lot of high resolution that brings out when we do that. And of course, in this example, you can see the turbines are placed actually in the higher wind locations, as you can imagine that the developers would like to use the higher wind locations. So if you stick to ERA5, you simply don't have the resolution to capture this kind of more local winds. So this is what we deploy. In the Chorus, we always scale the ERA5 with the global wind atlas for increased accuracy. And maybe on the next slide, I can mention a little bit that in addition to the high resolution, we also do in quite detail the power curves. We model different type of turbines, different type of hub heights. Also, we look at the specific power impacts. And maybe already I can go to the next slide to showcase that it's not just the turbine level power curve, but we put a lot of effort in getting wake losses correct. So if you build very large offshore wind, you get losses from 10 to 20 or even higher percentage. And we put quite a lot of effort in modeling those impacts on, installation densities, different type of turbines, and so forth. And then on the next slide, just to briefly say that if you want to look at this, like why do we put this extra effort in getting the VRE data correct? Put effort there, we put quite a lot of validation, and we show that there's meaningful increased accuracy when doing these wake losses in detail, getting the high resolution wind data from Global Wind Atlas. And here I focused on wind as it's kind of the core thing we do, but also similarly, we put quite a lot of effort in solar side, modeling tracking, model different installations, rooftop, kind of randomness in the rooftop rollout of tilt angles and so forth. And I think then I'm already ready for the final slide, I think, in my part. So here is just to remind that, I went through a little bit on the modeling, but here if you want to take a deeper look, because obviously this time is only for a general overview, we have provided 3 entries in the scenario. So we have this VRE data, the time series, the costs, land availability, and driven potentials, and so forth. over 40 years. You can find that in this Zenodo. There's a little bit of maps, solar, offshore wind, onshore wind capacity factors that are then used in the energy system modeling and the scenarios in Mopo. But then we also expanded that with a second entry. So we model the same under climate change. So you can look, okay, climate change under a few models. And then we did also a more detailed study for the Baltic case study that goes into detail into the Baltic countries, adds higher geographical resolution and also temporal resolution to showcase that we can increase the resolution as well. I think, I don't know if there's, okay, now it came back, but that's it from my side. And I think we move to hydro next.
Thanks, Matti. Can you hear me? Can you hear me?
Yes.
Okay, great.
Yes.
Hello, everyone. My name is Ilio, and I am a PhD student from KDH. What KDH has contributed to this Pan-European Dataset task is the hydropower. And we have developed 2 tools to generate the hydropower models in BDSON level. And these tools are published in GitHub repository. So the first tool is to generate the energy equivalent inflow. And the second tool is to, based on the equivalent inflow, to build the equivalent parameters for each area's hydropower. And we have also created a BDSON level hydropower dataset shared in Zenodo, including an estimated weekly reservoir inflow and daily run-of-river inflow for weather years 1980 to 2023. And we have also included the equivalent reservoir-based and pumped storage hydropower parameters for each area. And next slide, please. Álvaro, please go to, yeah, thank you. And to use the tools, the usage details of them are listed in each repository README. You can follow the setups to run both. The basic idea of the first tool is to retrieve the Era5 globe fast weather data based on the power plant location from OpenStreetMap, and then use the derived historical inflow from SOE and the other open access data platforms to train the model by regression, and then to estimate the inflow time series data for the weekly resolution and hourly resolution. And the second tool focuses more on the simulation aspect, which aims to build an equivalent hydropower model to mimic a given hydropower generation time series. The tool can be used flexibly if you don't want to run a complicated hydropower with very high computation time, but want to have a simple equivalent representation of that. So what you need to do is to feed to this tool to the detailed generation as like 1 year generation time series for the reservoir based or for the pumped storage hydropower, and then you can get the mimicked, let's say, virtual hydropower plant for yours provided time series data. Next slide, please. Yes, so as the setup of the 2 tools might be heavy, you can also directly download our simulated result based on the 2 tools for European bidding zones from the Zenodo. And the first one is EU parameter data. Now it's version 1, and we have, for example, for the reservoir-based hydropower, we have a maximum and minimum capacity and max and minimum discharge and ramping constraint and inflow digester factor. And then for the second one, it's a time series data set for the reservoir inflow and the run-of-river flow. And this is in a weekly resolution and daily resolution, respectively. That's it for the hydropower. Thank you.
Yeah, now we have for biomass, Tomi.
Yeah, hi all. My name is Tomi Lindroos, I work at VTT, and we contributed a regional biomass dataset for this project. We have actually 2 datasets. One is about the energy and another is about weight, depending which one you want to use. We provide roadside costs for both databases, euros per unit, and we do share the data in Zenodo. There's the link, and we also share a code to recreate or improve in GitHub. If you switch to next one, I'll tell a bit what is inside. So we have 3 main data sources. And the biggest one is S2 Biome. It's a EU project. Most of the data comes from there, and it's reprocessed. The original form was difficult, and now it's a modern in a modern form. And we integrated with Espresso and some national data sources to bring in the missing data pieces. And we provide energy and weight for over 50 different biomass categories on a NUTS 3 region. There's a caveat, so it's 2030 NUTS region, but the shapefile is provided in the repositories. We provide aggregation keys to other NUTS regions and NSOE bidding zones and aggregated biomass categories. So on the right-hand side, you see that we give figures for forest biomass, agricultural biomass, other land use. That's not a big one. It's mainly like trimming, cutting, roadside and stuff. The second residues from wood industries, second residues from agricultural, bio waste from municipalities and waste from wood, and also non-woody biomass sources, for example, animal fats, manure, other biomass, biosludge. But the main bulk is about the forest biomass and the agricultural biomass. And to better understand what is inside, we provide some Julia mapping tools, so you can draw your own maps. And we provide an Excel that compares these resource estimates to actually used amounts, because the database has a technical availability, but that is far more than what we, according to current knowledge, can use sustainably, or what, for example, the EU land use change regulations allow us to use. So when using this database, remember its technical potential, and not all that is allowed to use either politically or sustainability reasons. But then the last one. Here is a quick example of two figures about the content. So what I said about the technical potential versus the current production. So the higher figure has a fraction of unused potential. So looking at the whole country numbers, we see that most of the European countries seem to be using only 40% of the technical potential. Some countries a bit more. And especially the lower figure shows that a lot of forest biomass is not utilized as much as it could technically. But you can use this to get national estimates, regional estimates, and also the finer details of what kind of biomass. And we do not provide transport costs, because we don't know where you would be transporting this biomass. So it's the roadside costs. But there are a lot of generic sources for transport costs. For example, the IRENA estimates a range of 10 to 15 euros per megawatt hour, not asking from where, how, or why, or when. And then the second source is more precise. So it has a lot of data splitting the transport cost to variable distance costs and fixed costs. It gives this kind of data for various transportation modes, including trucks, rail, ships, pipelines, and that you can use to build your own transport functions when you are modeling. And these work in ton kilometers. So if you want to use this more detailed version of transport costs, you also must use the ton-based database. But yeah, was that the last one, or did I still have one slide?
It's the last one, yeah.
Yeah, thank you.
You're welcome, Tomi. Tars, your turn.
Yes, thanks. So here we are talking about energies, resources, conversion technologies, and storage. Well, the very short version is just here we are using the PIPSA data, so the power plants matching. So I'm not going in too much detail there. You can find all of the information at PIPSA. So instead, we'll focus here a bit on what you'll see when you are setting things up. As Álvaro in the beginning said, you have your data source, the blue box. You have your tool that extracts the data in the red box, and then in the pink box we have the eventual data that will be sent to the Ines builder in your workflow. So as for the data, we have here a lot of tool arguments. You see the power plants from power plants matching. You see the costs from the technology data repository from PIPSA, and then some other configuration files and such. And we'll go into detail about that a bit later on. For your Power script, you'll be needing the scripts that you'll find in the data pipelines GitHub that also some other tools use. That has also been shown a bit before already. And then once you are using that, you have all that data, you're using a script, and then what you get in the Power database is then all of these technologies that are then aggregated for the different countries in your shapefile. I think that's the most important stuff to say here. So in the next slide, we'll talk about this configuration stuff. So what can you do with these things? So first we have the geo level. So you have the GeoJSON file, which also can be found, I think, in the database repository, or you'll have to provide it yourself. Most likely you'll have to provide it yourself because it's a bit case study specific. If you're doing the European case study or the industrial case study that we have in our Mopo project, then we're using different GeoJSON files, and you'll have to provide that file as well as the geo level that you want for that. And then all of these power plants from the power plant matching file will be aggregated to that level. There are some technologies that you can choose in that configuration file, but these are partially hard-coded. That is because the power plants matching file is not very clean, so you have to do some sort of mapping, and we did that mostly hard-coded. But if in the future there is some kind of case that you want to do, and there's some kind of technologies that you want to consider, then then you can always raise an issue, and we may be able to bring it either to the configuration file or add that inside of the script. Then also under the hood and in the configuration file, it makes a distinction between a few years. The first two are based on like what is the data formatted in, which is 2020, and what is the data it should be formatted in is 2025. So with the inflation factor, we convert that. And then the other ones are the more related to the case study that you're doing, like what is the base year of your existing units, which is here also 2020, and which are the milestone years for your investments planning in your case study, which is 2030, 2040, 2050. And we are currently, that's inside of this configuration file, but we're planning to make that joined with the configuration file of the case studies of the Ines builder. But okay, for now it's like this. Then in a final slide, we talk a little bit about the data sources. So I already said it's from PIPSA, where we use the power plant matching file for the existing power plants, and we use the technology data repository for the future costs. And then with the inflation data, we then adjust all of these costs and numbers. Now the PIPSA data is very nice and very good to have, but there are sometimes some issues with using that. So on top of that, we have an assumption files that covers some of this missing data. It also overrides some of the data if we think that it's not suitable for the case study that we're doing. And that's just in this assumptions file. So you can look at the assumptions file and see what data is overwritten. And then it also covers a bit more data on carbon capture and hydrogen fuel, which are also a bit underrepresented in the PIPSA data. And with that, you can start using this one, I suppose.
Thank you, Tars. We are going to move forward to the electricity transmission. So, Muhammad.
Yeah, hello, everyone. Can you hear me?
Yes.
So I am Mohammed Numan from UCD and working as a senior power systems researcher here. And in the Mopo project, we contributed mainly to two parts in the Mopo project. One is the electricity transmission data, and the other is the development of the network reduction tool. So in the transmission data, we use the cross-border transmission data for the planning studies, and it includes all the transmission capacities of the different countries in the NUTS 2 region. So it's mostly related to the cross-border data. And for the whole European network data, we use the OpenStreetMaps data. And that is used also in the network reduction tool. So for the electricity data, right now, we only have the cross-border data that is used in the model. And the second thing is we developed a network reduction tool. So what it does, it's available in the, it's an open source and also available the link in the description. So it's an open source tool that is used to reduce the network while maintaining the electrical characteristics as same as to the original network. And we have added a lot of different functionalities that can be used to make it more flexible to users' requirements. So you can have a high resolution network of one area and you can reduce the rest of the networks. And you can have data available in multiple sources. So you can use the different case studies in the model. And it uses the concept of the PTDFs and total transfer capacities and using the optimization for the calculating the equivalent capacities of the reduced network. So the tool itself is available online and open source, and we have provided full documentation of the tool, how it works, how to install, how to run the case studies. Everything is there in the documentation. And we have also provided 5 to 6 case studies ranging from a small case study like the IEEE case 6 bus case study to a larger network of the 2000 bus systems, and also for the European case studies, which is like around 7,000 buses. And then you can use the tool to reduce it to your own resolution. So you have the option to select whether to reduce the whole network or reduce one part of the network and work as a full network, full resolution from the other regions. So it has a more flexibility for users, so they can select different options, and the model also have different options, different optimization approaches. So you can use the linear programming, quadratic programming, and also the mixed integer, depending on the use case studies, whether you want the binding or the congestion patterns. And also it has the visualization. So after the model, the tool works, it gives you a network visualization of the map and provides the original network and provides Excel files to have a complete analysis of the original network and the reduced network. And yeah, so this is the tool that we have used, and we are also trying to improve it to include further functionalities in the tool so that it can be used for a wide range of audience to reduce the network and used for it in other networks, other case studies. Yeah, there was a question or something.
It seems that there was a hand raised, but not now. If you have any question, please don't hesitate to ask. Muhammad, Everything is covered?
Yeah, for me.
Okay. Thank you. Thank you so much. So the next pipeline is the gas sector. This I will introduce this pipeline, but this task was led by Fluxys, by our colleague Virginie Pinson. So this pipeline basically is covering the methane sector, hydrogen sector, and also a bit of carbon dioxide. In the methane sector and also in the hydrogen one, so we are using mainly TYNDP data, so data from NSOG. And we are representing this sector, the methane one, using cross-border network. We are representing the existing capacity of LNG terminals, gas extractions, and imports. For the imports, we are modeling the capacity, but also we are considering an exogenous price for external or for methane from outside Europe. Also, we are modeling the underground storage. We have capacity for injection without roll, and also the capacity of the storage and cost for those injections and extractions. And finally, also we are representing new alternatives in this sector to produce methane, for example, biomethane routes and also synthetic methane routes. For example, the biomethane through biomass gasification, biomass digestion and upgrading, or in the synthetic side, for example, methanation to produce methane from hydrogen and carbon dioxide. In the case of the network, investment are not allowed. So the main idea is that the network is fixed, basically. In the hydrogen one, we are representing also the cross-border network, but in this case, we are using the projected reference grid by 2030 that has been used in the latest study of TYNDP 2024. So we are using this reference grids by 2030, and also we are considering potential investment in that network based on the different projects that are detailed in that study. Also, we have modeled underground storage using salt caverns, in this case considering potentials in Europe and the existing grid or the existing facilities by 2030. And finally, we are modeling also using the Danish technology catalog different technologies to produce this hydrogen, for example, in the way of using electrolysis, gas pyrolysis. Also, we are using, we have data for steam methane reforming and steam methane reforming with carbon capture. And finally, for the carbon dioxide, I mean, right now, it is not modeled very well. I mean, it's just we are considering that the CO2 is a global node in the model, where basically you can transfer CO2 across Europe, of course, with a price, and you have some kind of underground storage when you can inject this carbon dioxide, for example, with an annual sequestration capacity. But the idea is to extend this to a real CO2 network. And to do that, we have the report of the GRC about the potential CO2 network in Europe. So the main idea is to create something very similar, just to illustrate the impact of the CO2 transport around Europe to those underground storage facilities where it's going to be sequestrated. And finally, you can find here the sources that we have used for this data set. And that's all. So let's move forward to the next pipeline, which is the fuel transport.
Thank you.
Jussi? Yeah.
Thank you, Álvaro. My name is Jussi Ikäheimo, and I work as a senior scientist at VTT. And I will talk about fuel transport, which is also called cargo transport. So we have the pipelines in the model, but there are also other shipping modes, such as maritime shipping and road transport. And we need cost estimates for these shipping modes. So we set out to survey these costs for methanol, ammonia, and hydrogen. They are the most well considered renewable fuels in the future. And in addition, we also considered the costs for CO2 transport. Basically, this is a literature review using scientific articles and technical reports. The problem was that a lot of this source data just provide very simple total costs for the transport costs. But in our model, we wanted to make a model with broken down cost components so that it's easy to create different scenarios. For example, in the recent months, the cost of diesel fuel has gone up maybe 50%. So this kind of change can easily be fed into the cost model and see what is the effect on the transport cost. And what I can say is that the numbers just include the transport now, not any additional steps like conversion into the shipping state, like liquefaction. The results are available in units of per energy and per distance. And this is a function of the transport distance, of course, but it's not a fully linear function. Well, you can easily understand that for example, if you just transport fuel by over a distance of 50 meters by truck, there's still quite a lot of costs, so it's not close to zero. But in the cost model, the user can select this transport distance and then get the results. In the deliverable 2.2, you can find some background information about these calculations, and then the cost models itself are available in Zenodo. And then in the Pan-European Dataset, these per distance costs will be multiplied by the proper route distances. And on the next slide, you can see some results. So on the top, you can see the road transport results, and on the bottom, shipping results. And then on the left hand side, you can see broken down cost results, and these are per mass. And then on the right side, you can see the total cost per energy. So for example, you can see that there's a huge capital cost when transporting pure hydrogen. And for shipping, this is of course just an estimate, because there's no existing shipping of liquid hydrogen. When you consider the cost per energy, then the situation is balanced out a lot, because the energy content of hydrogen, so there's actually not so much difference in these different fuels anymore. Okay, that's for the fuel transport. Thank you very much.
Thank you. Thank you. Now we move forward to the end use or demand side. So we are going to start with the industry. So I don't know if Pieter is here or.
Yes, I am. So hello everybody. My name is Pieter Valkering, working in VITO Energyville, based in Belgium. We have been working on the Mopo industry technology catalog, and I'm going to say some words about that. So the point of departure here was an open source database called HRES, where you see the reference, which is still like the core of the data set further developed under the Mopo project. And it's the core, say, of the data set focuses on the most energy intensive process industries that you see here on the slide, covering steel, fertilizer, chemical, with 3 variations, basically olefins, polymers, and organic synthesis, the glass sector, cement, and refineries. And you can already go to the next slide. And just to really understand what is in the database, if you go to the next slide, there are sort of 2 main aspects to bear in mind. So on the one hand, it's about production volumes. So that means the locations and the volumes where these commodities are being produced. For example, where steel sites are located, and where the chemical plants and clusters are located, and so on. So that's one aspect. And then the other one is to have the data on the different ways to produce those commodities. So there is standard included a reference route, which say typically is based on fossil fuels with significant CO2 emissions. And in the database, in the technology component, you can find different alternatives based, for example, on clean molecules, based on carbon capture and storage, or based on electrification, or any other possible alternative to produce the same thing, but with less or no carbon emissions. So you will typically find them the production routes are characterized like by the specific energy consumptions, by vector, the amount of CO2 captured and emitted, and also the investment and operational costs. So if you go to the next slide, so what we did under Mopo, and what's now the overall data set, is that we focused a lot on creating a comprehensive data set. So whereas the original data focused on only the most energy intensive sectors, for energy modeling, it's important to have a full system coverage. So we combined different databases together, and mainly we've been working with JRC IDs, and also to some extent extracting data from Pipes Europe to create a full kind of consistent overview of all sectors, where the most important things are covered at the highest level of detail, but it's also covering other sectors that are maybe not as energy intensive, but they are still included in the database, sometimes at a lower level of detail, for example, not at NUTS3, but at a country level, but still being present. On top of that, we have been working a lot on improving the detailed data set for the Netherlands and Belgium in view also of the industry cluster case we do in Mopo. So this is what the industry technology component is, and then some last words on what you can do with it. There are 2 main things I would say you can do with it. You can use it as if you go to the next slide, as a standalone tool. Because if you provide, say, exogenous assumptions on energy prices, on carbon prices, and so on, you can use the data set as a standalone tool to generate data or demand scenarios for different energy vectors. So here you see an example how it was used to generate hydrogen demand scenarios that are further used to analyze hydrogen infrastructure requirements. Something similar you can do with carbon capture and carbon capture infrastructure. So that's one feature, and the other, of course, is to use it as part of a broader energy system model where you endogenize these energy production and energy prices, which are currently being demonstrated in the Mopo project. So that's it about the industry tool.
Thank you
for the next one.
Pieter, thank you. And the next one is the buildings. So Topi.
Yes, hello. I hope you can hear me. Let me know if you don't. But yeah, my name is Topi Rasku. I'm a researcher at VTT, Finland, and I did the building sector or heat sector data set more broadly for the case study, the Pan-European case study that Álvaro has been working on. So let's get into it. First, a brief bit of motivation. So why? Well, space and water heating accounts for a pretty significant part of the European final energy demand and represents a key sector for the energy transition. And for the work I carried out in this project, the main goal was basically to form a Europe-wide data processing workflow for heating demand and some supply side things as well, primarily for energy system modeling purposes. The data sources, there are a lot of data sources I had to scrape through because, well, if you've ever had the displeasure of trying to find comprehensive, good quality data sets about building stock and its properties across EU, you might know that it's a bit scattered. Every country does things a bit differently. And yeah, so on the right there, I have a rough illustration of the scope of the data set that I was able to pull together. So for the green countries, basically all I needed was available, whereas for the yellow countries, I had to basically project some parameters from neighboring countries to arrive at a reasonable data set, whereas for the red countries, there was not sufficient data available to actually make reliable data. Technically, it would have been possible to project some sort of heating and cooling demands for these countries as well, but it would have been based on really rough extrapolation from neighboring countries and bottom-up modeling, so the results could have been all over the place. I decided it's not worth the effort. So, Álvaro, please, next slide if you like. So, yeah, to kind of highlight the key outputs from this exercise are basically time series for heating and cooling demands for the different EU countries, as well as heat pump coefficient of performance time series. The data set that Álvaro has been made for country level because that's where most of the data is. But technically, it is possible to use the tools that are also openly available, that are shown on the figure on the right, to do this kind of estimation for an arbitrary geographical area. The tools are not as very easy to use, but they are technically capable of that. As well, the other key output is a rough estimation of heat-only generation capacities, like existing capacities in different countries, as well as a sort of projection of how they retire across the few next decades. But this is a very rough estimate. But to quickly maybe explain the figure a bit on the right, there's a lot of data on the left that first goes into this ambience to ABM, which is basically a pre-processing for the data to get easily machine readable building stock data that then goes into this archetype building model, which is the sort of primary package that models or simulates the heating and cooling demands as well as the heat pump COPs. It also, of course, takes in some GIS data about the distribution of the assumed distribution of the building stock, weather time series from ERA 5, etc., etc. And like I mentioned, what that produces is the time series themselves. But unfortunately, this kind of bottom-up modeling for the building stock is very heavily dependent on the quality of the building stock data, which for this kind of a wide area is not very reliable. So it is better to use top-down projections to kind of normalize those time series to more reasonable values, or more, maybe I should say, reliable values, which is what the last tool does, which is this Mopo heat sector data processing, which takes in these future heating cooling demand projections from hot maps, EU project results, also uses or includes the sort of heating sector data or parameters from Danish energy catalogs. And then for the heating device capacity mix distributions, it relies on JRC IDs data. And what comes out of this is basically the final data set for the case study done by Álvaro. And like with the rest of the stuff presented, these tools are available in GitHub. Their inputs and outputs are available in Zenodo, the ones that have been used in the Mopo project, in case you're interested to check them out yourselves. But yeah, that was me. Thank you. And I believe it is Omar next with transport.
Yeah,
Yep.
Omar. Thank you, Topi.
Yes. So
sorry, we have a slide here from I think the industrial sector. I don't know if Pieter wants to say something, but sorry, Omar, because
no worries.
Perhaps
no, please skip it. It's an accident that it's there.
Okay. Thank you.
So essentially for transport, what we did, we developed a new tool, Chapeau EV, which stands for charging profiles of electric vehicles, which links scenarios for you define scenarios for various cases, such as the European case study or the industrial regional case study. You run it and you obtain profiles, and essentially those scenarios, they tell you where vehicles will go, so where they start and end, how they travel between those locations, and how often, based on a number of statistical elements. And we define it first for a base case, which is based on the Netherlands, because that's where we started. And then we vary either per region or per country. In principle, you can vary everything, but in practice, there were 3 parameters that are a determinant. One is the vehicle consumption, typical vehicle preference consumption. So how big of a car people want. And that's based on the emission factors of gasoline and diesel vehicles. So then you can figure out what preferences they have in a given location. It's based on the number of hours worked per week and per year. So essentially how often you do commute, and the typical home work distance commute. And then you can scale, and then you can obtain from one scenario, you can make 30 for each European country, and then change it if it changes per year horizon, or don't zoom in for a region and account for regional differences. Essentially there it will be the home work commute distance. Once you have those scenarios defined, then you compute a mobility matrix, mobility patterns, which tell you at each hour, which is the resolution, where the vehicles are, if they are moving from one place to the other, if they are parked, if they can charge, etc. And that gives you a mobility pattern. From that mobility pattern and combining with the vehicle properties, you can figure out a consumption, which is the baseline is electric, but of course you have also equivalents in other fuels, so that we can provide also weekly or monthly or whatever consumptions for other fuels. And then we focus on the electric part. which will then, once you have a demand, then you have to satisfy that demand in a certain way, and that's where you compute the charging modules. And if you go to the next slide, then I'll explain that a little bit more. What we provide is two types of profiles, or two elements. One is what standard profiles for vehicles that are not managed by the network operators. So they are either just arriving somewhere, once they plug in, they charge at max value until the battery is full, or you could have some adaptive charging, but based on their own behavior. And that includes also possibly having modulated charging. So if the available power diminishes, but on a set pattern, then you have also that's part of that. And the other part is you provide boundary conditions if you want to manage that charging. So you want to say you are an operator and you say, well, I'll provide you charging based on status of the network, my costs, or anything else. And for that, you need to put boundary conditions, restrictions, so that those are satisfied. So essentially, it's the demand of the vehicle when they leave. So you have vehicles that are about to leave, and they need to arrive somewhere. So they need to have at least a certain amount of charge. You need to provide also what's possible in terms of what you can deliver, and that depends on how many vehicles are connected and where and which power they have. And that gives you an efficiency. And then you have also an efficiency of that charging power, because what you provide from the network is not what the vehicle gets, not always. And if you have those boundary conditions, then you can compute, you can make a model within your optimization model, which is shown here. And that gives you what managed and optimized profiles are. And if you say, well, that percentage of vehicles are not managed and that percentage of vehicle is managed, then you combine that and you have an effective profile, which have been provided. So we provided the tool itself, the inputs, and the outputs as well on Zenodo and GitHub, two repositories, one for the model itself and one for running, so including assumptions and some tweaks to obtain the results. Yeah, that's it. You're on mute, Álvaro.
Oh, thank you, Omar. Sorry. Thank you. Yeah, and thank you to everyone for attending. So we have explained all the pipelines now, and we have an intuition and also details about how we got this data, and also how we transfer the data to be usable by the European dataset and the purpose of this dataset, which is basically energy system planning for now. So now what we are gonna do. So basically, I'm gonna show you because that would be the most interesting part. So I'm gonna show you how to use this dataset and how to get all this data and use it in the Spine ecosystem. So of course, to do that, we need a Spine installed. But there will, so for those who are not familiar with the Spine, no worry, we are going to have a webinar in 2 weeks about the Spine tool and well, the whole Spine tools on how to install. So that's a good reason to attend to that webinar. But right now, just trust me, and I will show you how to import this dataset. So first of all, what I'm going to do is just show you where this dataset is. So this dataset is in Zenodo, and basically is collecting all the data that we have talked about in this webinar. But also we have here all the data pipelines that we have used to process this data and to get ready this data for an energy system planning model. So how do we use this dataset? First, what we need to do is just download this dataset from Zenodo. It's a zip file that basically contains all the raw data, the data pipeline, so Python script to process this data, raw data, and create the intermediate databases. And it has also a model builder that is basically using the interoperable energy system specification that has been developed in this project. Once you basically download this webinar, this dataset, basically what you will see is this. It's a folder that has the .spine toolbox folder, which is the spine project to be used. So that is needed to be used in the spine ecosystem. Also, we have a data folder. So for those people who are only interested in the data in the raw data that we are producing in this project, this folder is that raw data and can be used. So you can take it and use it in a different way. Also, we have the data pipelines and the geodata, which is basically the GeoJSON files that we are using in Mopo, so to represent the spatial resolution that we are using in this project. And also, we have a set of Python requirements for the different Python script that we use in the data pipelines. So to use this, so let me close here the project. So for those, once you install the spine ecosystems, you will see this. This is the spine toolbox. It's a graphical user interface where you can basically drag and drop items to create a data workflow for different purposes. So what we are going to do here is just to simplify everything is we go to file, and then what we can do is open and then open our Pan-European dataset. But this is the folder, but you should unzip from the file that you are downloading from Zenodo. So when you unzip and then you open the file, the dataset in Spine Toolbox, what you will see is this. Okay, so this is the whole workflow. And as I explained at the beginning of the presentation, so what we have is a kind of satellite here, which are data connections, data connection points that basically those items are pointing your the raw data in your laptop. So basically, it's pointing the data folder in the Pan-European Dataset folder. And then what we do is basically import that data or point that data to be read by each data pipeline and each Python importer. So what it's doing, this Python tool that we have here. So if you open this tool, you will see that this is a Python script. So basically, it's reading the raw data, processing the data, transforming the data, and loading the data in this database. This database is an SQLite database that has a DB editor, so where you can basically manage, check your data, modify your data, do whatever change. So basically, this script is reading the raw data, which could be a CSV file, Excel file, and importing this data into a specific structure here in this SQLite. This structure has been predefined by myself. I mean, I did it. And then basically what I do with the Python script is import everything in this format. And why in this format? Because I mean, it's more readable for downstream processes, for example, to create a model. So we are basically creating a model in a way that basically we define each element as a potential entity, and then we have an entity which could be a generator, another entity which could be a node, and then we have a relation which is a generator connected to a node. So that is the way that we model we create the models in the Spine ecosystem, in the Spine node, but also in Guinness. And there, basically, you can check all the data that we have for all the pipelines. So, for example, if you go to the VRE, you will see that this database that contains a lot of time series, it's more heavy. So it will take more time. But of course, we have 42 weather years of time series. So it is more gigabytes, but it's readable. And then you can inspect and also have a look at the different parameters with this SpineDB editor. Also, you can plot the different points. Of course, I mean, as we have a lot of data here, it's not readable, but you can see how this is a capacity factor for a wind onshore technology. So, and you realize how it looks. So these are the data pipelines, and also what we have here additionally is the INES builder. So the INES builder is building the model in the interoperable energy system specification that we have developed in Mopo. So the main idea is to create an INES model that is able to be connected to other tools. In the Spine ecosystem, we have a Spine app, which is our energy system optimization tool. But the idea is to create different transformers that can connect to other tools, for example, like PyExa, where you have but of course we need that transformer. But the idea is this dataset is interoperable and could be used in different tools. So this INES builder is a Python script that is reading each database and basically is creating the model based on, of course, based on a mapping that we have developed. For example, we should map that, for example, a generator, the efficiency of a generator is equivalent in INES format to a parameter which is called efficiency, and an entity which is called unit instead of generator. But if you want to learn more about that, when you open the INES database, but right now it's not created. Sorry, it's not imported the template. But basically, once you run for the first time the INES builder, you will import the structure of the INES database, and basically you will explore the different parameters that it has and also how to model different entities. I have dropped in the chat a message with the INES specification where you can explore what it is and how it models the different things for energy system. And finally, what is the structure of this? For the last item of this workflow is the INES input, which is basically a user configuration file. It's a user configuration file where the user can define which pipelines wants to model, and also spatial resolution, some kind of which planning year you want to model, different things. I think that I can show you a little bit more about this user configuration file. It's a YAML file where basically you can activate or deactivate pipelines that can be imported to your INES model. So in the case that you specify that a pipeline is false, it's not included, it's true, it's included. And then I have added different details here. For example, what is the source resolution? So what is the resolution of the raw data? And what is the target resolution of your for that pipeline? Okay, so in Mopo we have developed a different spatial resolution, or we are using different spatial resolution, which is country resolution, PCD2, which is a sub-regional resolution that ENSO uses, and also we have NUTS2 and NUTS3. Most of the data is at country level, so if you wanna use a different high resolution, then we will apply different transformations to that data based on some assumption. For example, demand, you can use population. In the case of capacity, you can use area. It's not accurate, but I mean, it's a proxy. So that's the idea. And also, there are some pipelines where the source resolution is, for example, NUTS3 as the power sector 1. So if the source resolution is NUTS3 and your target resolution is country level, then basically we add the different parameter. For example, if the parameter is capacity, if not, we apply a different transformation. So also you can model basically the resolution of your model, operational resolution, planning resolution, which target year you want to model, and also which are the units of your model to scale the parameters up and down. So also to avoid numerical issues in the optimization part. Also, you can interact and also modify the weather years that you are importing in the different pipelines. For example, if you remove these two weather years, basically what we are doing when we run the workflow and the pipelines, we import only this year, 2009. But again, it's a way to do it. Also, we have in this user configuration file different global constraints which are related to basically carbon budget constraint. Also, the main idea is to include more parameters here which are aligned with the European climate policy. For example, a renewable energy target or a hydrogen production target. And finally, the countries. So in the case that you want to model Europe, that basically in this data set is EU27, Norway, Switzerland, and United Kingdom, then you can basically write Europe. But if you want to model, for example, Spain, then you need to use the country code for Spain and for France. And then in this case, what you are modeling is two countries, and those are Spain and France. What happens if you model, for example, different sectors at different target resolution? Then basically we apply a kind of connection, or we create a kind of connection for those different resolutions. For example, you can have hydro systems at country level and the power sector are NUTS 2. What happened? That basically the hydro system, which are at country level, can basically supply energy to all the different regions. That's an assumption, but it's something. I mean, it's just to avoid a different setup, or in case that people want to see more detail or want to evaluate more details in different regions and in different countries for a specific sector. And finally, if you explore this user configuration file, we have the part of the commodity where basically you not activate or deactivate. Basically, if you define true or false, you are defining that commodity, it's a global commodity or is a country-specific commodity or regional-specific commodity, depends on the spatial resolution. For example, if you define false for methane, basically you have a global node of methane in your model. And also the type, the node type, which is basically what type of commodity you are implementing. It's a storage node. It's a balanced node where basically you supply and then you get demand, you get energy for demand, or it's a commodity. It's a kind of node where you only extract energy. You can inject, but there is no balance. So that's the idea. Also, we have also a layer for the network in case that you wanna include or not the network. The same for storage and for technologies. But in the case of storage or technology, you can impose a kind of investment method. So basically, if you include that technology, that means the status parameter. If the investment method is not allowed, basically you are setting that you cannot invest in that technology, so the investment variable is 0. But in case that is no limits, you can invest whatever amount of capacity. If you have cumulative limits, it's okay, but be aware that you need to model the corresponding parameter for that cumulative capacity for that specific technology. And that's all basically from this side. And this is an overview of the dataset. Of course, there are a lot of things that we cannot explain in this webinar, but in case that you are interested, please don't hesitate to contact us, to contact any partner of the consortium, Mopo, or reach out to me. And also, there is a documentation available for this dataset that everyone can use it, and basically explain you how to use it, how to set up your framework with more details, and how to even it gives you an explanation of the data. It gives you details on how to run this framework using a spine up, and how to even visualize your results. So I think that's all. We can conclude here this webinar. And Lars, you have a message for the next webinar?
Well, I think it has basically been covered, but I'll just quickly repeat. So indeed, in the next time we will be talking about installation of Spine Toolbox, Spine Opt and such. None of what will be said there will be new. It's all available online in the installation instructions and etc. But in case you like someone to see how it needs to be done, well, then that's the place to go. And also the focus of that webinar is going to be a bit more on questions. So if you had issues with trying stuff out, with doing some stuff, you can go there and ask some more general questions. It doesn't have to be only about the installation and such, what will be covered there, but it can be just more in general about spine tools. So if you're interested in that, see you there. And otherwise, hopefully see you in one of the other ones.
Great, thanks. So that's all. Thank you so much for attending to this webinar. Hope to see you in the next one.
Yeah, thanks. See you.
Bye.
Bye-bye.